Good morning. Hi, Katharina.
Morning. Hey.
So I'm going to introduce the next speaker. That's Katharina Dücker. So now we're going to change gear a bit and think more about electrophysiology and how that linked to neural computation and also artificial neural networks. So I've had the privilege of working with Katharina. We have been doing a project together with Marco Idiot, and the idea is to take artificial neural networks and then try to introduce more realistic temporal dynamics. So that's Katharina. She did her PhD here at the Center for Human Brain Health, and now she's at Brown University continuing on computational neuroscience. But nevertheless, it's a great pleasure to have Katharina here, and we are very much looking forward to your presentation.
Yeah, thanks, Ola. So you kind of you've given the introduction to my talk. So as Ola just said, this is a project. No, it's not working. This is a project that we did with Marco Idiot and myself and Gerben in the Netherlands. And the idea is to explore how oscillations may help with neurocomputation in artificial networks. So as you may know, electrophysiological recordings from the human brain done with EEG or MEG, usually non-invasively, are dominated by alpha oscillations. That's 10 hertz oscillations over the back of the head. I hope you can see this video. This is actually a recording I took from an MEG recording, and as you can see, they kind of come on, they turn on and off. It's very high amplitude in some people, about 10 hertz rhythm. Here it is again. And these rhythms have been associated with rhythmic inhibition. So we know that depending on when you present a stimulus relative to the phase of the oscillations, participants are relatively more or less likely to see the stimulus. So there are certain phases in the oscillation that are associated with perceiving a stimulus better or worse. And similarly, with this idea of functional inhibition, there's also been work showing that strong alpha oscillations here shown as coherent. So here I want you to look at this red, blue, yellowish band at around 10 hertz. When that activity is relatively strong, then firing rate, here shown as the black line, is relatively weak, and vice versa. And this was actually work done in somatosensory cortex, but similar things have been shown for other cortices as well. So the proposed idea, or the proposed mechanism, that the proposed role that these oscillations may have been playing is that they might allow multiplexing in visual cortex specifically. So while it might seem a bit counterintuitive that the brain would rely on this inhibitory mechanism, we wanted to explore what the benefit would be of those. So as you may know, the visual system is said to have a hierarchical and converging architecture. So we know that early visual cortex can process several stimuli in parallel, while the higher order cortices, object selective cortex and feature selective cortex, they seem to be doing this multiplexing, whereby they switch between the activation of stimuli that are presented simultaneously. So imagine you have two pieces of fruit, like we obviously in the visual world, we often have two or more stimuli presented very in close proximity at the same time. So imagine here you have two pieces of fruit. Your inferior temporal cortex has very large receptive field, so it's very likely that at any one time, two or more stimuli could be in the same receptive field. So in this case, a passion fruit and an apple are competing for visual resources. And now the idea of how oscillations may help in this competition is that if you are attending to one of the stimuli, say you want to buy a passion fruit, so you're looking for a passion fruit, then all neurons responding to the features of that passion fruit should be more strongly excited. So you have an inhibitory oscillation. Again, neurons responding to passion fruit features receive strong excitation. So in feature selective cortex, those neurons should be able to overcome this inhibitory threshold at a slightly earlier phase than the neurons responding to the unattended stimulus. And through this mechanism, the idea then is that as the passion fruit neurons activate, they are then turned off by refractory dynamics, so that the neurons responding to the apple can take over. And by the time the apple is processed in feature selective cortex, the passion fruit has already made it to object selective cortex. So this is sort of this multiplexing idea paired with a pipelining mechanism that is timed by inhibitory oscillations. So the idea was to have a computer vision network that shows exactly this pattern. Okay, so I want to emphasize here that this is proof of principle. This is merely showing the idea and how it works and exploring these dynamics. So because of that, the network is relatively simple in comparison to all the networks that are out there at the moment. So we have two fully connected layers, a converging architecture. So the first layer is larger than the second layer. And the input is read in by a convolutional kernel that is moved over an image in steps of quadrant size. So it first takes in the first quadrant, then the next quadrant, then the next quadrant, then the next quadrant. And what that does is it leads to competition in the process between the quadrants in processing these quadrants. And the network was trained on one stimulus at a time. So each stimulus presented in each of the four quadrants, and we had three letters, A, E, and T. And you can see within about 7, 8 epochs or so, the network is able to learn these stimuli. Again, it's likely that the network has overfitted this problem. That's not so much the concern. The concern was more to provide the idea. Okay, so here are the activations post-training for each letter. And what I want you to see here is, well, one, the network can do it, right? We have the readout, the network reads out the letter in the corresponding output node, so A, E, and T. And what I also want you to see is that in the hidden layers, the activations are somewhat sparse. They're also somewhat binary. That is by design, but they also overlap. So we can't just read out, if we were to present two stimuli at a time, we can't just read them out like this, because they do have some overlapping representations. Okay. After the training, we replaced each network node with a set of ordinary differential equations. So after the training, we added on some oscillatory dynamics to this network. And we did this by, instead of having one value H, one activation value H between 0 and 1, H now follows a time course, whereby it changes according to this function. So this might look a bit more complicated than necessary, but basically at each time step, the current value of H tries to approach the sigmoid activation of H based on the current input, that's ZG. And so through that, we don't just have one value for H, we have a time course. As H approaches its actual sigmoid activation, it is opposed by a refractory term R. So that is described in this equation. As you can see, R grows, is also dynamic, and it grows as a function of H. So as H gets closer to the value where it wants to go, R also gets closer, and we subtract it in the sigmoid activation. So in this way, the activation should be ramped down. And then we also added an inhibitory oscillation, which I'm going to call alpha, which again is subtracted. And you're welcome to look at the preprint for the actual tuning of the free parameters, but they were all tuned such that age would show dynamics in the 8 to 12 hertz range. Okay, here's what this looks like graphically. So as you can see, age is the blue line. Age goes towards 1. As it does so, R grows with a slight delay and brings it down. And through that, we have these dynamics in the 10 to 12 hertz range. And as soon as we turn on the inhibitory oscillation, we actually see that the node is entrained to the inhibition. So it's now oscillating in antiphase to the inhibition. Okay, here are the dynamics in response to a single input. So here I'm just showing the network NA, and this is without the alpha inhibition or the oscillatory inhibition. So as you can see, the output node corresponding to A turns on. But we also have some spurious activation of the letter E that is actually currently not in the image. When we look at the dynamics in the hidden layers, we also see that the nodes are quite different in frequency and phase, depending on the size of the input. So nodes receiving a strong input, that's the darker color, they oscillate at a slightly lower frequency, but have very high amplitude, and very small inputs oscillate at a higher frequency, but they're lower in amplitude. And then layer 2 is, again, it's a bit more synchronous than layer 1, but again, there is a phase shift between them. And these plots show the limit cycles. So we see we have some oscillatory behavior that oscillates around the fixed point, which is a bit less stable, the limit cycle behavior in layer 2. Okay, as soon as we add the inhibitory oscillations, things really start to clean up. So now we have a higher synchrony between the input nodes. We see that the ones that receive relatively strong inputs are in phase, and they seem to have the same frequency, and the nodes that receive relatively weaker inputs are a bit lower in frequency. And very nicely in the output layer, we see these dynamics entrained to the 10 hertz rhythm. So the output node A activates an antiphase to the inhibitory oscillation. So now, just to show you that the network also cannot recognize 2 stimuli at a time, or that there is congestion in the network at all. This is just the non-dynamical network. And this is the response to 2 stimuli at a time. So if I train the network on 1 stimulus at a time, now I show it 2 stimuli, and kind of as expected, it spreads out the activation in the output layer over the two corresponding nodes. And these are the dynamics without any refraction, and you can sort of see that the activation in both nodes ramps up following this time course TH or tau H, sorry. So now things get more interesting when we add the refractory dynamics. That's the middle panel here. So again, I'm showing 2 stimuli at a time. I'm making one a bit brighter and one a bit dimmer. That's sort of mimicking object-based attention. And what you can already start to see emerging here is that the output nodes start oscillating in antiphase, and they seem to alternate between the corresponding stimuli. So the orange line is the output node for letter E. That turns on first, which is good because E is the attended stimulus, and then letter A turns on. We already see some switching, some multiplexing behavior. The dynamics actually seem to be running away, so they're somewhat unstable. But just adding refractory dynamics to the hidden activation has already helped a lot. Same for the combination of T and E. Now, as we add the alpha inhibition, we're going to call it, or the inhibitory oscillations, what we actually start to see emerging is a phase code, similar to the one that I showed a couple minutes back. So we see the attended letter E activating first, and then starting from the second cycle, we have E being read out first, and then it's turned off by its refractory dynamics, and then actually A can take over. Similar here for the combination of T and E. So this is to show that adding these dynamics based on refraction and inhibition has actually created the pattern that we sort of proposed it would. I've very early on, I've told you that early visual areas are set to be able to process stimuli in parallel, whilst later areas show this multiplexing switching behavior, and that also happened to emerge in our model. So here is the, oh, sorry about this wide bar, but here's the activation in the first layer. And what you can see is that in antiphase to the inhibitory oscillation, the whole network almost seems to switch on. And when we look at the representation, it actually appears that both T and E, both letters in the image, are represented or can be read out from this. So both letters are turning on, neural representations of both letters are turning on at the same time, whereas in layer 2, what you can see is that there's actually the network is activated more sparsely within one cycle, and that's where this multiplexing, the switching between the two stimuli already starts to emerge. And then obviously, as I've shown you in the output layer, then the switching is quite clean. Okay, to sum up, what I wanted to show you today is that when we train a network on one stimulus at a time, it cannot cope with two at a time, or rather it spreads out the activation, suggesting that there is some congestion when reading out these two stimuli. When we add refractory dynamics to the network, we already see some switching, some alternating behavior between the two stimuli presented on the screen. And when we add pulses of inhibition or alpha inhibition or oscillatory inhibition, however you want to call it, we see this temporal code or this phase code emerging in the output layer. And yeah, with that, I'm happy to take any questions.
Yeah. So thank you very much. You can hear me, right?
Yes, I can, yeah.
Yeah. So let's see if there are some questions from the audience. So Yali has a question.
Yeah, thank you for the nice talk. Very simple question. How do you decide on the number of layers? And does it relate to the temporal oscillations? For example, if you have more layers, your frequency band go down or up, something like this.
I don't know.
That's interesting. Yeah, no, I heard that. So the question was if how I decided on the number of layers. So well, the first prototype of this, I just had one layer just to try it out, and it wasn't really stable. So changing the parameters changed the behavior of the network very dramatically, which in hindsight, now looking at this graph kind of makes sense, because in this multiplexing really only emerged when I added another layer, and then it was more stable in the second layer. So that kind of made sense. The dynamics in the node depend on the parameters that I've chosen. So they strongly depend on this tau here and this tau here, which defines sort of the rise time of the activation H and the refraction R. It also depends on C, which obviously the higher C, the more R will grow at each iteration when we solve these ordinary differential equations. So it's not so much to do with the number of layers. However, yeah, I think it's something I would have to check if I have a very deep network, if it would sort of in the output layer then slow down. So I'm not 100% sure of that.
But maybe also to comment on this, so this is early days, but the big advantage of this network is that it has real time, and this real time we can match to human brain activation. So of course now we have a few layers in, but say you have 10 layers, then you can ask how long does it take for the network to then get to the end, right? So if that takes longer time that we can measure from the brain that it takes to do the decoding, there's an issue. So what I'm trying to say is that we can now do parallel experiments, and then we can use the activation in brain to constrain also the architecture of the network, for instance, in terms of different layers. Yeah.
Have you tried optimizing the performance of your classification based on these parameters, like the strength of the oscillation and the amount and strength of the adaptation?
Optimizing in what sense? You mean like have a cost function for, yes, I don't know, temporal codeness, for example?
No, for whether the network can indeed decode which letters were presented as the input. So you present the A and the B letter, and then you say, does it correctly classify it? Because you showed it can't, when without it you can't do it, right?
Yeah, so I mean that's kind of the point, that it can't do it. We could have.
So the question is then, what are there optimal parameters for making this work best? Because it seems a fairly strong regime, which, well, to be honest, I've looked only at monkey data and most single cell recordings, but it's very strong oscillations that you might not expect perhaps in the real brain. So, or maybe you say it does happen, but I wonder how soft you can make this and it still works.
You mean soft as in the activation being more sparse and maybe more noisy?
So in terms of the alpha drive, can you turn that down so it's just sort of tickle the system a bit? Would that be enough to synchronize it?
Yeah, I mean there is a range, right? You can slow the code down. You can, if you increase the amplitude, it will only read out one. If you decrease it, it will read out more. So so that the cycle will become longer. So those type of things, yeah, one could do. Obviously, I mean, these values don't make sense in like an electrophysiological way. I get that. That was also, yeah, matching it to those type of amplitudes was kind of also not the point. It's more the how strong the oscillations are relative to how strong the activation is, if that makes sense.
Okay.
So sort of beyond Katharina's modeling, one can ask these oscillations, do you see them, for instance, in the cranial recordings in monkeys? And there's a debate to this because for decades, alpha oscillations were mainly reported in humans, whereas non-human primate physiologists did not really see them. But now there's more recent work, first by Beth Buffalo, where they have been recording in the deeper lamina of cortex, and then there you see the alpha oscillations, whereas many monkey electrophysiologists record more in the superficial layers when the neurons are doing the coding. So part of this sort of funny discrepancy between strong alpha in humans, little alpha in monkeys, might be explained by where the electrodes are. So now if one is using laminar electrodes and look at the deeper layers, then you actually see a strong fingerprint of these oscillations. More
And
questions?
there's also an ongoing debate on where they are where they are generated and where they are emerging. So there are also people saying that they are generated actually also generated in the supragranular layers. But through volume conduction, we see them quite strongly in the deeper layers. So there's also this debate.
Yeah, I mean.
I guess you look at how close the symbols are and how much interference you have in the activation. Because if the symbols are too dissimilar, is it easier to get the right synchronicity? And so, for example, if you had an A and maybe an O that looked very similar in shape.
Yes. So, I mean, again, this is more of a prototype. I did try and use the MNIST data set on this same network, and there it can't produce a code, which I think is because the network doesn't have enough layers to represent and orthogonalize the representations of these letters. So if I present an MNIST and I don't know, I show a 6 and a 9, then the network thinks it's looking at an 8 and does not read it out as a code. So that's actually something that I know Marco Iliad has been working on to sort of orthogonalize, like think about how long should we presenting these two stimuli in parallel, and when should they then merge. So that would depend on the architecture, but this particular architecture cannot do that.
More questions? Okay, then thanks again.
Thank you.